Hello and welcome. My name is Ariel, and I recently decided to start a YouTube channel where I can talk about things I like and care about, and basically to try to improve my conversation skills. This is my first video. I'm using Zoom to record this. I tried using OBS, but it kept ruining my audio, and then I realized I can record myself on Zoom, and it seems to work well. I'm also using Camo Studio to record video using my phone's camera and have it stream to my computer. So the video of me that you see right now is actually being captured by my iPhone. And the reason I'm doing that is because the camera on my computer is not great. So for this video, I'm going to talk about a geometry problem that I found online, and I'm going to show you how I solved it. Actually, I'm going to show two solutions, but we'll get to that. Here is the puzzle in question. I found it on a YouTube channel called The Phantom of the Math, and I got this thumbnail from their channel. I didn't actually watch their video, so any similarities between my video and the Phantom of the Math's video is completely accidental. Just a little disclaimer. Anyway, the striking thing about this problem for me is how little information is given. So what we have here is a square and a quarter circle inscribed in it with radius capital R. Then there's also a smaller circle with radius little r that's tangent to just two of the sides of the square. And then there's this red line, which is tangent to both of the circles. That means it just touches the circles without going through them. And we're given that capital R minus lowercase r equals 10. And that's all the information there is. And based on just that, we have to find out the length of the red line. It seems at first like not enough information. I mean, we don't know the side length of the square or either of those two radii, but it turns out that the length of the red line is what's called an invariant in math. That means that the length doesn't change regardless of all the other variables. So let me show you how I solved it. Well, the first thing I did was draw out this diagram for myself, and I don't like using capital letters for side lengths. I usually use lowercase letters for side lengths in geometry. Usually uppercase letters are used for vertices and areas. So instead of capital R, I'm using lowercase s over here. And then the next thing I did was I labeled all the vertices, and also I made these little ticks over here. So the side lengths AB, AG, and AD are all equal because they are all radii of the large circle. And then I focused on the smaller circle here, and we see that the smaller circle touches the side length BC and the side length CD. So I drew two line segments from the center of the small circle to each of those sides, the point of intersection between the circle and each of those sides. And we label each of those, call them I and J. And then these two angles have to be 90 degrees. Why? Well, because the each of these side lengths, BC and CD, are tangent to that circle. And so that means that the line segment from the center of the circle to the point of intersection has to be perpendicular to that line BC. And I'm not going to prove that right now, but that's a theorem from geometry. So this angle is 90 degrees, OIC, and so is angle OJC. And also the angle ICJ is 90 degrees because that's one of the angles of the larger circle. And Because these three angles are all 90 degrees, that means that this other angle over here, IOJ, also has to be 90 degrees. Why? Because this is a quadrilateral, and all the four angles in a quadrilateral have to add up to 360 degrees. And furthermore, these two side lengths, OI and OJ, are equal because they're both radii of the smaller circle. And so that means that this shape, OICJ, is a square. Now, that might seem obvious just by looking at it, but in math, you have to do everything 100% rigorously. You can't just say, oh, this looks like a square, therefore it's a square. No, you have to explain why. So then after that, I drew these four lines over here, and you'll see why pretty soon. And then I colored these four regions like so, and I wanted to show that each of these four quadrilaterals that I've colored is actually a kite. So first of all, what is a kite? Well, it's similar to the kind of kite that you're probably familiar with, like a kite that you fly. And it's a quadrilateral with two pairs of equal adjacent sides. So I'm going to go enlarge that a little bit. And now so for the blue shape here, for example, we have AB equals AG. So that's one pair of equal adjacent sides. And I want to show that EG is equal to EB as well. So how do we know that? I'm just gonna enlarge the screen here a bit. There, now we have more room. And we see that this brown line, AE, it divides that blue shape into two right triangles. So this angle here, angle AGE, has to be a right angle because that red line is tangent to the large circle, and the angle ABE is also 90 degrees. Why? Because that's one of the angles of the square. So we have two right triangles, and since they're right triangles, we can use the Pythagorean theorem. So we have AG squared plus AE, no wait, AG squared plus GE squared. So I'm looking at the triangle AGE is equal to AE squared. And in the second triangle, we have AB squared plus BE squared equals AE squared. So in both of those triangles, we have AE as the hypotenuse. So that means that the left-hand sides of those two equations are equal to each other. And like I mentioned earlier, we have that AB is equal to AG. So first of all, let's combine those two equations. So we have AG squared plus GE squared equals AB squared plus BE squared. And then we can use this. So we can replace AG with AB. Is it still recording? Okay, yeah, it's still recording. Not sure what happened there. Anyway, AB squared plus BE squared. And now we have AB squared on both sides of that equation. So we can cancel those out, and we get GE squared equals BE squared, or GE equals BE. And now we have what's called side-side-side congruence between the two triangles ABE and triangle AGE. So they have the side AE in common, and they have AB is equal to AG. And now we see that they also have a third pair of equal sides, BE is equal to GE. So that means that those two triangles are congruent. And in fact, each of those four colored regions is a kite, and the brown line in the middle of each of those divides that kite into equal, congruent uh, right triangles. Now, I'm not going to prove the same thing for each of those because that'll take a while, but we have a similar argument that we can use. I'm going to clear my drawings there. So, so basically what we have here is BE equals GE. So that's from the blue kite. Then in the green kite, we get that FE is equal to EI. Then in the pink kite, we get FH is equal to HJ. In the orange kite, we get GH is equal to HD. All right, now remember, our objective is to find the length of the red line, which I've labeled as EH. And in order to do that, I'm going to divide that line EH into two line segments. So let's divide it along the point F. And since E, F, and H are all collinear, they're all along the same line, so we can divide EH and say that EH equals EF plus FH. And we can do the same thing for the point G, since EG and H are also collinear. So we have EH is equal to EG plus GH. And now we can add those two equations to get 2EH equals EF plus FH plus EG plus GH. And now we're going to use each of these four equations to rewrite that equation over here. So we have 2EH, replace EF with EI. Whoops. Then we replace FH with HJ, replace EG with BE, and GH with HD. And now look what we have here. We have EI and BE. Now the points, or the vertices BE and I, are all collinear, as you can see here. So that means that EI plus BE can be rewritten simply as BI. And similarly with HJ and HD, those 3 points are all collinear. And hj plus hd equals simply jd. So let's rewrite that equation up here. But now, what is bi equal to? Well, it's almost equal to the length of the side length of the square. And there's just this part over here, which is equal to the side length of the smaller square. But the side length of that smaller square is the same as the radius of the smaller circle, which is r. And what's the side length of the large square? Well, it's equal to s. Oops, sorry. So that means that, sorry. So BI, I don't know why it keeps malfunctioning like this. All right, I'll try to just use my mouse. So BI is equal to S minus R. And what about JD? Well, it's the same thing. It's equal to the side length of the large square minus the side length of the small square, and that equals S minus R. And what is S minus R? Well, we're given that at the beginning. It's equal to 10. So we have 2EH equals 10 plus 10, which is 20. And that means that EH is equal to 10. And that's it. The red line has a length of 10. That's what we needed to prove. Okay, now I promised you that I was going to show you two solutions. So without any further ado, here's the second one. And in this solution, we're going to be investigating the area of the shape that's created with those four brown lines that I made earlier. So the area of AEOH. And we'll call that area fancy A. So what is it? How do we find it? Well, we can divide that quadrilateral into two triangles. We can divide it into triangle AEH and triangle EOH. And for the area of each of those triangles, we use the formula base times height. So for AEH, the base is equal to EH, or sorry, base times height divided by 2. And then the height is AG, which is equal to S divided by 2. And then for triangle EOH, it has the same base, EH, but the height is FO, which is the radius of the smaller circle, which is equal to R, and divided by 2. So now we can factor out EH divided by 2, and we're left with S plus R. So that's fancy A. And if we multiply that by 2, then we have EH times S plus R. So why did I multiply that by 2? Well, if we take a closer look at this shape, AEOH, It actually contains exactly one out of each pair of colored triangles. So see, it contains AEG, that's one of the blue triangles, contains one of the green triangles, one of the pink triangles, and one of the orange triangles. So if we multiply that area by 2, then that gives us the total area of all of the colored triangles. And so 2 times A would be the total area of each of those colored regions. And what is that total area? Well, it's almost the same as the area of the large square, which is S squared. But there's this other smaller square, which is not part of any of the kites. So that means that the total area of those 4 kites is equal to the area of the large square, which is S squared, minus the area of the small square, which is R squared. But now S squared minus R squared is a difference of squares, and oh, you might not be able to see that. Okay, I'll rewrite it here. It's equal to S squared minus R squared. And now we can rewrite S squared minus R squared using the difference of squares formula, like so. So that means that we have the following formula. EH times S plus R is equal to S plus R times S minus R. And then we can divide both sides by S plus R. Notice we have S plus R on the left-hand side and the right-hand side. And that just leaves us with EH equals S minus R, which we know is equal to 10. So once again, we got the same answer. It's equal to 10. And in fact, there's nothing special about the number 10. We can just say that EH is equal to the difference between the radius of the large circle and the radius of the small circle. So that's it. That'll be all for this video. Thank you so much for watching. I apologize for those few issues that occurred. Hopefully, as I make more videos, I'll be able to avoid those issues and make these videos run more smoothly. But yeah, that's it for now, and I hope to see you all next time.